my name is Alex, and today I wanted to share some knowledge on large language models, also known as LLMs. LLMs power applications like ChatGPT, Google's Bard, and Cloud, basically revolutionizing how we interact with AI. But what are they, and how do they function? In this presentation, I'll explain the core concepts and advanced techniques that allow LLMs to generate human-like text, answer questions, and help with various tasks. I aim to make this complex topic understandable for everyone, regardless of technical expertise or background. So I hope that after this presentation, you'll have a good understanding of what LLMs are and gain some contextual knowledge needed to optimally implement and leverage these models for your needs. We'll dive into the key areas of the definitions. First, we need to understand exactly what is what. Then we can jump from that and talk about how these systems perceive and process information and the architecture behind LLMs, especially the transformer model. We will also cover important concepts like embeddings, tokenization, and prompt engineering, and hallucinations. We'll finish off by exploring the various applications of LLMs. First, we need to get our definitions straight. What is artificial intelligence? Originally, artificial intelligence, or AI, is the driving force behind computational systems that mimic human intelligence. It's about machines that can learn, solve problems, perceive the world around them, and adapt all through the use of advanced algorithms, data processing, and machine learning techniques. Whereas we have LLMs, LLMs are a specific kind of AI that uses deep learning to process and generate human-like text. They rely on enormous datasets and have billions of parameters that allow them to understand and summarize and predict content. LLMs are like the engines that power sophisticated language-based tasks, enabling a wide range of applications from chatbots to content creation. LLMs run on a combination of statistics, mathematics, and computational algorithms. Now, if we will go a bit deeper, to support these powerful LLMs, we have transformers. A transformer is a type of a neural network architecture. The transformer concept was initially introduced in 2017 in a research paper titled "Attention is All You Need." This paper was authored by a team of 8 scientists from Google, and the transformer architecture is based on the attention mechanism. And it marks a significant advancement in natural language processing and has been widely adapted in various AI applications. Transformers are highly efficient in processing sequences of data, capturing long-range dependencies without the need of recurrent connections. They use so-called layers of self-attention, allowing them to model relationships and data efficiently. This architecture is what makes it possible for LLMs to handle complex language tasks effectively. To make these concepts more relatable, let's think about the analogy of vehicles, where AI is like a broad category of vehicles. Everything from trucks to buses falls under this umbrella. Large language models are the cars, a specific type of vehicle designed for a particular purpose, just as LLMs are designed to process and generate language. Finally, we have transformers that are like the engine inside a car, a crucial component that drives the car's performance. So again, AI can be metaphorically associated like a vehicle. It is a very broad range of human-like intelligence, whereas large language model is a particular subset of those vehicles. In this particular example, it is a car. And a thing that actually runs this car is the engine. And the engine are the transformer models. We can see how they all fit together to create the AI systems that we interact with today. As we dive into the comparison between AI systems and human understanding, it is essential to recognize that despite their impressive capabilities, AI and humans' approach to understanding is fundamentally different. In more simple words, the way these systems perceive information and the way we perceive information are different, and that does not necessarily mean it is a bad thing. First, let's consider the key differences. AI systems don't possess true understanding of concepts like a dog, a job, or a bank. They build perceptual relationships. To phrase it more correctly, they build perceptual relations based on data that they process. But this is far from the reach. Layered understanding that humans achieve, meaning that the depth of understanding in perception that human beings have is much more broad and much more information consistent in humans than it is in AI systems. For us, understanding is not about recognizing patterns. It's about linking those patterns to our experiences, emotion, and personal significance. Think of how you remember the last time you were on a vacation. You cannot rewatch or relive every moment with exact detail. Instead, you hold on to snapshots, sensations, and impressions. So some memories are vivid, kind of vague, while others are influenced by their emotional and experiential context. When it comes to AI's understanding, of the perception process, it begins with tokenization. This is where AI breaks down information into numerical representations, creating vectors that represent words and concepts. It is just a way that these systems are efficiently able to think. Through AI breaks down information into numerical representations, creating vectors that represent words and concepts. Through pattern recognition, AI rebuilds associations based on statistical relationships learned from vast data sets. It's a purely data-driven process, devoid of the emotional or experiential dimensions that shape human memory. So AI's memory is essentially like a vast library of facts, interlinked by probabilities and numerical relations, but without deeper meaning, without any context behind them. So to illustrate this difference, let's use an analogy of object recognition. Humans can easily distinguish difference between objects, like a car and a cake, thanks to the repeated exposure and the contextual understanding that comes from experience. You not only identify a car, but you can also instantly connect it with related concepts, meaning roads, maintenance, speed, travel, and so on. AI recognizes these objects by identifying patterns and associations in a numerical way, but it lacks the broader understanding of what a car truly means in context. To make this more simple, it only sees the data representation and the data connection between objects. Whereas a human being has many layers of memory that would include contextual memory, emotional, experiential, and many others that give context to the events that took place. So, in conclusion, while AI can simulate understanding through advanced data processing techniques, it lacks depth of context and experiential learning that characterize human cognition. The difference the difference lies not just in what we recognize, but in how and why we understand what we do. AI may form connections and recognize patterns, but the nature of the depth of these processes are fundamentally different from our human experience. I would like to dive a bit deeper on how data associations work and give an example on how statistical associations are created for words based on different contexts. So that is the perceptual side for AI. This is a very simplistic approach, but it should give you a foundation for perception of this concept. Let's say we have 5 sentences, and all of them combined are considered our single sample space, meaning it is the beginning and it is the end. So it is a complete sample space. Let's say we'll use the word books, which will be our focus word for this demonstration. First, let's talk about co-occurrence. So we have these 5 sentences, and we identify the key um, in a word that we identified as books. It is just a word that I picked. But if we are trying to understand how it correlates to other words, we need to talk about co-occurrence, which is key to this analysis. Co-occurrence refers to how often words appear together within a context. So in our example, we are examining which words frequently appear alongside books, the word books. This basic idea is crucial for understanding more complex language relationships in the field of NLP or natural language processing. To calculate the associations between books and other words, we count how often each word appears with books across our sample space and divide this count by the total of occurrences of books. Now, I know this may sound complex, but hang on with me here. I'm sure we're going to get to the end. So, this results in a probability that shows how likely a word is to co-occur with books. Visualizing these associations with a chart, if you would look on the right, the word science has a 60% association with books. It means that in our sample, books appear in a context related to science 60% of the time. Meanwhile, library have a 40% association, appearing with books less frequently than science, and so on with other words. From creating the from calculating the probability for each word and each relation that we have, we will be creating a system, not a system, but we will be creating a co-occurrence matrix shown on the left here, on the bottom left. A co-occurrence matrix basically illustrates how often each word in our dataset appears with every other word, serving as a foundation for calculating statistical associations and analyzing language patterns. Each cell on the diagonal line shows how many times the corresponding word appears in total across all sentences. The cell where books intersects with books shows 5 because books appear in all 5 sentences. So they have the most co-occurrence. For science, the diagonal shows 3, as it appears only in 3 sentences out of 5. Library also shows 2 on its diagonal, appearing only in 2 sentences. Interestingly, these associations change context. In our sample science, the words science and library are highly associated with books. However, in a bookstore or school context, words like fiction or homework might become more strongly associated, highlighting the importance of context in understanding word relationships. While our example is simplified, real-world language models analyze vast amounts of data and use complex algorithms to determine these associations, with co-occurrence being a fundamental method in helping these models understand the relationships in the world. Large language models utilize these statistical associations to predict and generate contextually appropriate text, even without truly understanding the actual meaning. By understanding word relationships in various contexts, LLM produce human-like language, despite lacking true comprehension. As we refine these techniques and expand the data that LLMs learn from, we are getting closer to machines that can communicate in a way that's almost indistinguishable from human language. Now let's dive into the architecture of transformer models, which are at the engines of many modern AI systems. Input processing, we can see the model on the right there, is a process that begins with tokenization, where it breaks down our text data into smaller units called tokens, which could be words or subwords. This step is crucial as it converts raw text into a format that a model can understand. Attention mechanisms are, let me try and turn on the cursor here. So this is basically the encoder block, and this is the decoder block. It doesn't tell you anything right now, but just hang on with me and you'll get a bit of clarity. So attention mechanisms are, this is where the magic happens. Attention allows the model to weight weigh the significance of different words in relation to each other. Basically, it's like the model that we were just looking at on the previous slide, but in a more larger scale. It's like the model is deciding which words to focus on to understand the context better. Interestingly, we call this multi-headed attention, which works like a multi-headed hydra from Greek mythology. Just as the hydra, can look in multiple directions at once, so the multi-head attention allows the model to focus on different aspects of input simultaneously. Each head can attend to different parts of the sequence, capturing various types of relationships between words. Of course, the hydra analogy is a metaphor that I use, but I think it is an easier way to visualize this. We have a layered architecture in a transformer model, and transformers, they use multiple processing layers, meaning that there is not one, and each layer refines the understanding of the input, capturing increasingly the complex relationships between words and concepts. And all this happens in parallel processing. Unlike earlier sequential models, transformers, they compute inputs simultaneously. So this parallel approach dramatically speeds up the processing and allows the model to handle longer sequences of text efficiently. But it comes at a cost of a high compute consumption. And finally, we have the output generation, which the model predicts the next words based on all the processing that has happened. This is how it generates text that seems coherent and contextually appropriate. So looking at the diagram, you can see how these components fit together. The input, embedding, and the positional encoding feed into a series of encoder layers on the left. These layers process input text on the right. These layers process the input text, and on the right, we have a decoder layer. And the decoder layer, it generates the output, taking into account both the processed input and the previously generated words. The multi-headed attention blocks you see are hydras in action, and they are the model's key ability to understand context from multiple perspectives. The feed-forward networks and normalization steps help in processing this information further. At the top, we have final linear and softmax layers that convert the model's internal representations into probabilities for each word in its vocabulary, allowing it to make predictions. So this architecture allows transformer models to capture long-range dependencies in text, understand context deeply, and generate human-like text with remarkable fluency. It's this design that has revolutionized natural language processing and enabled the creation of powerful language models like ChatGPT. If we were to visualize that process in a more simple way, we could get an understanding of how the prompt is being injected into the workflow. We're going to talk about prompts in a more deeper context a bit later, but I just want you to see where the prompts come in and how they work with this system. This diagram illustrates the key components we covered earlier. This is basically the same representation of the transformer model that we've seen on the previous slide, but in a more simplified way. We start with the raw input, which could be a query. So when you type in a prompt or insert some data into the large language model, this data goes through the embedding block, where each token is converted into a vector representation. The embedding block also incorporates positional information, allowing the model to understand the sequence of words. The encoder block, represented here with multiple cubes and hydra-like symbols, is where the multi-head attention mechanism we discussed previously comes into play. Each head of the hydra represents different attention mechanism, allowing the model to focus on various aspects of the input simultaneously. This is repeated through multiple layers, refining the model's understanding of the input. The decoder block works similarly, and but with an important addition. It not only performs self-attention on its own outputs, but also attends the encoder output. This cross-attention mechanism allows the decoder to generate outputs that are relevant to the input. The output layer then processes the decoder's output, typically through a feed-forward neural network and a softmax function to produce the final result. This could be the next word in the sequence and an answer to a question or any other form of text generation. You'll notice the model data cylinder connected to various parts of the diagram. This represents the learned parameters of the model, which influence every step of the process. So that is our pre-trained data. That is where the large language model gets the knowledge for the answer. Lastly, the context of conversation and embedded vector components illustrate how transformers can maintain context over long sequences, enabling them to generate coherent and contextually appropriate responses. So this is a simplified workflow that encapsulates the parallel processing, layered architecture we discussed earlier, showing how transformers efficiently handle complex language tasks. What I also wanted to note that it is crucial to understand that the embedded vector, which represents the context of the conversation, the embedded vector is generated from the raw input, if not otherwise specified, meaning that if a user isn't clear about the context, if the user isn't clear about the context they want in the conversation, the AI will infer it from available information or try to simply guess. Another point to note out is that everything you send to the large language models becomes a part of the data used for future responses within that single conversation, unless the proprietary model is using your data within your conversation for training purposes of future models. So what I'm trying to transcribe here is that everything you say to a large language model within a single conversation becomes a part of the data that is used for future responses within that single conversation. So it is crucial to maintain a single purpose within a conversation. For instance, if you begin discussing cats and later you start talking or asking about traveling, there is a chance that cat-related information might unexpectedly appear in responses about travel. The model might draw unusual parallels or use cat-related metaphors when discussing vacation plans, simply because the context of cats is still in the conversation history, is still in that dialogue. So, as the dialogue progresses, the LLM processes more data with each new input, referring back to previous exchanges to maintain consistency and relevance. Also, be mindful of the duration of your interactions. Extended conversations require increased processing power, and that may result in slow responses and potential context overflow. The relevance and clarity of your inputs throughout the conversation directly influence the LLM's ability to provide accurate and contextually appropriate responses. While the model is designed to identify context effectively, it is important to be as specific as possible about the intended context and the scope of the conversation overall to ensure the most accurate and relevant responses. Before we move on, we need to talk a moment about context. Large language models have an enormous amount of data in the backend, meaning behind the curtains. As mentioned previously, it is important to make your requests as specific as possible so that the model will look in the proper place. Imagine it is a huge base. Imagine image its knowledge base as being a huge library. In a library, we have sections where we have books, and where each book with appropriate context is assigned to a particular section of the library. When the raw input goes through the embedding process, the LLM is trying to extract relevant context from your question in order to understand in which section of the library, which is a multi-billion parameter dataset, in which section of that dataset it should look for an answer to your query. Let's consider an example. How do I prepare for an upcoming event? At first glance, it seems like a straightforward query. However, as we can see from various options listed, from company events to weddings, from cooking masterclasses to science, the term event can refer to a wide range of situations. So this situation creates uncertainty for the AI model. And this uncertainty is what the AI model faces when presented without context. Without additional context, the model doesn't know which specific type of event the user is referring to. So what does the human want in this case? If the context is not provided, then the model generally does one of the following. First of all, the model might provide a broad, general answer that could apply to various types of events, or it can try and guess the context based on previous interactions, or it will look for common usage patterns, meaning that what are the similar questions that the other users might have asked in relation to events. The AI might make an educated guess about the most likely type of event. Or the model could present several possible scenarios covering different types of events. And lastly, the AI might point out that the question is unclear or too vague and ask for specific information in order to fine-tune the embedded vector we mentioned previously. So, without proper context, the AI is left to interpret the query based on limited information, which may lead to responses that don't fully address the user's actual needs. But it is in a situation where it has to give an answer. So it is a reminder that while AI has made tremendous strides in natural language processing, understanding context remains a complex challenge that requires ongoing refinement and user awareness at all times. Now that we have an understanding of the importance of context, we can now add an extra layer, a definition to it. So, knowing how to structure and phrase the raw input, knowing what context to provide, and knowing what information to include or exclude, all combined is called prompt engineering. Prompt engineering, it is the art and science of crafting effective inputs for large language models to generate desired outputs. The crucial point to remember is that LLMs don't exactly speak human language. They process and return information in the form of tokens, which we will explore in more depth soon. So the best approach is to learn to communicate in what we might call LLM syntax to get the best results. An important thing to know here is that there is no single prompt engineering approach that can solve all your problems and work for every model and any type of prompt. Different LLMs process information differently. They have different data sets with different engines. They require different communication strategies. And LLMs have a tendency to change and constantly evolve, and their data sets expand, they're being retrained, and their engines are fine-tuned, and there is no one-to-all solution here. So the best way to master prompt engineering is to practice. Let's discuss an important phenomenon in large language models called hallucinations. Hallucinations in LLMs are instances where the model creates content that is factually incorrect, nonsensical, or inconsistent with its training data and the given context. These outputs may seem plausible, but they don't correspond to any verifiable information or logical inference from the input. The two main reasons hallucinations are related to the model's data and its architecture. It is crucial to understand that LLMs use generalization to create results. It means they don't simply recite memorized information, but they rather combine and mix it from the other training data to generate new content. We can think of this process as LLM dreaming, creating new connections and ideas based on what it knows. Sometimes these dreams or generalizations can lead to inaccuracies or inconsistencies. Just as human dreams can mix up reality and fiction, LLM's outputs can blend factual information with invented details or misrepresentations. This is why it's essential to approach LLM's outputs with a degree of distrust and verify important information from reliable sources. Now that we have a general understanding of the workflow of LLMs, let's take a look at how they see and think. Tokenization is a process of converting text into smaller units called tokens, which can be words, subwords, characters, to enable the model to process and understand the text efficiently. First, let's distinguish between words and tokens. Words are the basic units of human language that we, as humans, naturally understand. For example, in Hello World, we see two distinct words. Tokens, however, are more complex. Tokenization is the process of converting human language into data bits that a computer program like an LLM can understand and process. Tokens represent whole words, parts of words, combinations of words, or even punctuation marks. Look at the example on the left. When we read Hello World, we see a simple two-word phrase, but the LLM sees it differently. First, it breaks down into tokens, hello, world. Then, each token is assigned a unique ID number. These numbers are what the LLM actually processes. So each number corresponds to a specific token in the model's vocabulary. The image on the right, intended to show the perceptual difference and metaphorical assistance, I would say, an image posted by computer science Andrei Karpathy. Of course, the LLMs doesn't see everything in emojis. It is a metaphorical representation of tokens to show how things may appear different for humans versus LLMs. This is just a bird's view representation. We need to go in deeper into the woods to see what's happening under the hood. Now let's walk through an example of how LLM processes text from input to output. Input text. We start with the phrase London is the city. The tokenizer breaks down this phrase into individual tokens, like we saw in the previous slide. In this case, each word becomes a token. I have to note here that I break each down into an individual token for the sake of simplicity. In reality, the NLP models that are used within LLMs do it a bit different. But just for the case of this presentation, imagine that each word is a separate token. London is the city. Each token is then converted to corresponding token ID. Here we see that London becomes 1851, is number 8, the becomes 36, and city becomes 182. These token IDs are fed into the LLM, which processes them based on its training. The LLM output goes through a softmax function, which converts the raw data output into probabilities. The probabilities, the result is a probability distribution for the next possible word. In this example, we see probabilities for words like of, that, where, with, and in. This process illustrates how an LLM takes input, converts it to a format it can understand, that is, token IDs, processes it, and then outputs probabilities for the next word. The highest probability word would typically be chosen as the next word in the sequence. This example demonstrates why precise input is crucial. The LLM is making predictions based on the specific token, on the specific tokens it receives, and changing even one word could significantly alter the probability distribution for the next word. And here is a simplified layout of what is happening deeper under the hood during the decision-making process of an LLM as it generates text. Each column represents a token. Each column represents a token position, and each box shows potential words with their associated probabilities. For our example, London is the city. The model predicts probabilities for the next word, with the word of being the most likely one. The model simultaneously considers various continuations, expanding possible sequences for each token. It keeps track of probabilities at each step, effectively expanding the canary tree of possibilities. A canary tree is a tree data structure where each node can have up to k children. In the context of LLMs, each node represents a token, and its children are the possible next tokens. The k in the canary refers to the number of most probable next tokens considered at each step, also known as the bean width in beam search algorithms, but we're not going to go deep into that here. This process continues until we reach the desired length of the end token. The model then selects the sequence with the highest overall probability. Notice how probabilities change as we progress after of history becomes highly probable for the next token, if we compare it to this one here. In this case, London is the city of history and culture. London is the city of history and culture. Full stop. We got this result because for this example, we use only the highest probability return. This path of tokens represents the highest probability path. But there are alternative routes, and we can see other plausible continuations like London is the city that, London is the most popular, and so on. This probabilistic process explains why LLMs can produce varied outputs from the same prompt. It's not deterministic. Each generation involves a series of weighted choices. One important thing to note here is that if the model would always be choosing the highest probability values, we would be ending up with pretty much the same result each time we asked a particular question. So, in order to introduce entropy, or variability, if you may, into the system, a parameter called temperature was introduced. Temperature controls the randomness of the model's decision making. High temperature increases randomness and creativity. It makes lower probability choices more likely to be selected, leading to more diverse and sometimes unexpected outputs. Lower temperature produces more focused and deterministic output. It causes the model to more consistently choose the highest probability tokens, resulting in more predictable responses. This temperature setting, combined with the probabilistic nature of the selection process, is why LLMs generate diverse responses to the same prompt. It is also why small changes in probability or temperature can lead to significantly different outputs. Temperature is just one of several sampling methods used in LLMs. Others would include top K, nucleus sampling, but we won't be covering that here. Now let's try and run this example live here with a beautiful tool that can help us visualize this process. So we're going to be using the sentence that we worked with in our presentation. Notice that I'm going to be lowering the temperature just for the sake of this example. This is a very nice model developed just for the purpose of you to have a better understanding of how these things work under the hood. So now that we have generated the next token, in this case it generated 15, which seems quite odd. Oh, I'm sorry, I didn't click the generate button. So first of all, it reproduced the token the, and then it looked into its after running the model, it looked into its pre-trained data set, and it found that the word future is the most probable one in the context of data that the model knows and has. And that's why the next word predicted was future. There are other tokens that are available to this model, as you can see. But the model picked specifically this one because I lowered the temperature. Now, if I would increase the temperature, you can see that it starts to fantasize and it can go sideways. Yes, it becomes more creative, but in this case, it can generate sometimes inconsistent and very much inaccurate information. But this is a great way. I do recommend playing around with this tool. It's called Transformer Explainer, where you can visualize some of the processes that happen under the hood, help you better grasp the subject here. But overall, it works in line with everything that I mentioned previously in the presentation. So the main takeaway here is that LLMs have a parameter called temperature, which directly influences the results created by the LLM model. Let's explore the landscape and talk about the most common types of LLMs and some popular tools that exist in the field today. A small disclaimer. The number of AI tools that exist today is enormous, and the ones I mention are a personal preference pick and don't cover use case specific tools like LLMs that are used now for writing code. We have web-based LLMs. These are hosted on remote servers and accessed via APIs. Examples can include ChatGPT, Cloud, Gemini, Grok AI. They offer powerful capabilities but require internet connection in order to interact with you. There's another type of LLMs, and they are locally run LLMs. These operate on personal computers or servers without needing of internet access. They require a decent machine though to run on, otherwise you'll spend a while waiting for each response to be generated. Examples include Mixtral and Llama, my two personal favorite picks. They provide more privacy, the locally run models, because the data circulates within your machine, and this gives more control, but they have um, more limited capabilities than compared to their web-based models. And we have LLM development tools. These are frameworks and utilities that enhance the existing LLM capabilities. Examples include LangChain and Hugging Face. So unless you are a developer that works with AI systems, you don't necessarily need to know them. But it's good just to be familiar that these tools exist. These these LLM development tools, they help developers work with, um, customize and deploy LLMs more effectively. And there is also a type, a very type, a very interesting type of tool that I wanted to mention briefly. It is not an LLM itself, but it's a very interesting tool to know and use, which is called Perplexity. It is a very powerful AI-powered search engine, which basically helps you browse the internet using LLMs in a very efficient way. So if you haven't tried that out, I highly recommend it too. And finally, we have image generation models. And these models are created only for a singular purpose of creating images. And I find it personally fascinating with the things that can be made by using these tools. My personal favorite pick would be Midjourney. But there are also other models that produce quite an effective output. The variety of LLM types and tools is vast, and this is not a finite list. And every month, new AI research papers are released, and so do new AI solutions. If you want to be up to date with the latest model performance, a good resource I would recommend is called the AI Arena. The AI Arena is a platform designed for comparing AI models. It does this through head-to-head battles, which is a vivid way of describing direct comparisons between different AI models. Um, keep the The key point here is that the platform allows users to rank AI models. Let me try and open this one. So this is the chatbot arena that I've mentioned previously, and this is of September 3rd, 2024. We can see that currently now ChatGPT 4.0 is the leading model and it has the highest score. But these things is like the stock market. It changes quite frequently, and there is no single winner. Just a few weeks ago, Claude 3.5 Sonnet was on the top of the chart, and now it's sixth. So this is a very good resource just to stay tuned and have an understanding what exactly is the model good at, so you can see the particular ratings that they're given to these models. So I would highly recommend take a dive into it and have a better understanding of what's happening there in the arena. Let's take a look at the diverse applications of large language models across various domains. LLMs have revolutionized how we approach content creation and text-based tasks. They are not just writing assistants, but powerful tools for enhancing communication in multiple formats. In the scope of data and analytics, LLMs are transforming how we process, analyze, and visualize information. They are making complex data more accessible and actionable. Automation and customization have also seen significant advancements with LLMs. These models are streamlining workflows and integrating with existing systems. And finally, LLMs are proving invaluable support and assistance roles, from providing general knowledge to tutoring to offering career insights and skill assessments. What's particularly exciting is how these applications often overlap and complement each other, creating powerful synergies across different areas of work and life. As we continue to explore and develop LLM capabilities, we're likely to see even more innovative uses emerge, further transforming how we interact with this technology and information. We've covered a lot of ground today in our exploration of AI. Before we wrap up, let's take a moment to recap some key points that I really want you to take away from this presentation. First and foremost, it is crucial to understand that LLMs are, despite of their impressive capabilities, they aren't magical black boxes. They are sophisticated systems built on solid foundation of statistics, mathematics, and advanced algorithms. In essence, they are a product of rigorous computational processes. It's important to remember that LLMs are limited by their training data. They can only mix and match what they have been trained on, not create entirely new knowledge. How do LLMs interpret our language? This is where tokenization um, was discussed, and it's like the alphabet of LLMs. When we break down text into tokens, these models can process and generate human like language with remarkable accuracy. We have embedded vectors that we mentioned previously, which are central to how these models process and understand information. Think of these vectors as the model's way of capturing and representing complex relationships within data. This is how they see context in a given conversation. Self attention mechanisms and multi step reasoning capabilities. These features allow them to focus on critical information and tackle complex problems step by step, much like a human would. And here's a crucial point: the quality of the output depends on the quality of the input. If you're not getting the results you want, don't blame the model right away. Often, the key to improvement lies in revisiting and refining your prompts. One of the great things about LLMs is their versatility. Whether you prefer the privacy of running them locally on your machine or the convenience of web-based services, there is an option to suit your needs. Looking ahead, I'm excited to announce that my future videos will dive deeper into AI with focus on how to effectively leverage these AI systems in different contexts. These upcoming sessions will be more of hands-on experience. If you have any questions or would like to learn more, please feel free to reach out to me. Thank you for your attention today. I hope you've learned something new, and I bid you farewell.